All right, so today we're going to be talking about electrochemical cells. It's kind of the important or the usable, the most practical part for me of redox reactions. Okay, so taking these reduction oxidation reactions and actually making use of them. So typically when we talk about redox reactions, it's all about how sodium uh, gives up an electron, which is not negative, to become like positive sodium. Chlorine will take an electron to become negative chlorine. And if I put these things together, I've got sodium plus chlorine plus an E negative becoming the sodium ion plus the chlorine ion plus an E negative. I've got electrons on both sides, cancel them out. Really, I've got Na plus Cl. Typically, though, that would be Cl2. Taking 2 electrons becomes 2 there. That means chances are I'm going to have to double this stuff here. I know I'm going super quickly here. 2Na plus Cl2 becomes these things that know Na plus Cl is going to form together to become sodium chloride. All right, typically that's just a redox reaction. If you were to just combine sodium and chlorine just kind of in the air, in a beaker, in a container, it doesn't matter. Where these two things come into contact, the sodium's giving up its electrons, the chlorines are going to take those electrons to form these ions, which pretty much immediately become sodium chloride, table salt. Why that's important is what if that's not occurring in a beaker? What if we're just not allowing those electrons just to be transferred from one molecule to the next? What if we provide a path for these electrons to go through? So kind of what that would look like is, so the basics of an electrochemical cell. Essentially what we have is we're going to have two beakers or two containers. Okay, so let's say the actual reduction oxidation reactions I'm concerned with are silver involving the positive one ion taking an electron to become neutral, and nickel, the positive 2 nickel ion taking 2 electrons to become just neutral nickel. Essentially, an electrical chemical cell, kind of in its most basic form. So I've got two beakers. In each beaker, I'm going to have a strip of the metal that's in there. So let's even say this one's my silver. Put an Ag there, and this is my nickel, okay? This beaker has a strip of silver in it. This beaker has a strip of nickel, all right? And we're going to have a solution that these metal ions are in. Now, in the silver beaker here, I'm going to have this silver ion. All right, and to get that silver ion in solution, essentially I'm just going to take like silver chloride, silver nitrate, silver carbonate, silver phosphate. I'm just taking a silver salt, dissolving it in water because dissociation happens, and I'll get that silver ion to just be floating around. I don't really care about the negative ion in this case. I don't care if it's chloride or nitrate or, I just don't care what it does. All right. So that means over here, the solution that the nickel strips in, I'm going to have that nickel ion, so the Ni positive too. And these strips are just kind of sitting in this solution with their own metal ion in it. So now, if I want oxidation or reduction, typically you can't have one without the other. If Leo goes Gurf, losing electrons is oxidation, gaining electrons is reduction. Right now, there's nothing, electrons aren't just going to jump across the air to go from the silver to the nickel or vice versa, depending upon which one does get oxidized. So in order for this reduction to occur, I need to connect my metal strips with a wire. Metal, copper, silver, gold, doesn't matter what your conducting material is, even like steel wire I think could work. It just needs to be a wire that connects them. Right now, I could get like a couple of electrons transfer and then things will stop because at that point, you're going to have an imbalance of ions. So if I'm curious, if I want this electrochemical cell to be useful, I need to be able to maintain kind of the neutral charge here that's kind of in both beakers. So that means I kind of need the ions to be able to kind of fix themselves. So the other thing I'm going to put in here is I'm going to put a salt bridge. I think it's easier just to use, sodium chloride, NaCl, as the salt bridge. And you're going to see why here in a little bit. All right, so I've got my electrical chemical cell all set up here. Now we need to figure out of silver and nickel, which one's actually going to undergo reduction? Which one's going to undergo oxidation? And to do this, you need to check a table of the reduction potentials. If you Google reduction potentials, you'll find some really, really good charts. If you're in class, you'll be getting one from there. And essentially what we're going to do is we're just going to look for these two reactions. The first reaction, silver, +1 plus 1 electron becomes silver. All right. So the reduction potential, the shorthand for that is this kind of capital E with a superscripted 0. And if I find that on that chart, I should find that this has a reduction potential of, I'm even going to add the positive there, 0.8. And these things are actually measured in volts, okay? If I check the nickel one, I get that this will be negative 0.26 volts. All right, so, okay, we found these numbers. How does that help me at all? Well, what this measures actually is how likely is it to undergo reduction? Essentially, the rule is the bigger the number. So if you kind of think of it like if I kind of have a number line here, we're going to make that -10, and this is +10. The bigger my number, the more this way I am, the more likely I am to undergo reduction. So in this case, this one's pretty easy. I have one positive number, one negative number. The positive one's the bigger number, so that's going to be the one that undergoes reduction. And gaining electrons is reduction. But the way that this is written, this is already written as a reduction reaction, okay? And since this one's positive, this is my reduction reaction. Now this, the nickel reaction, is still written as if it's a reduction reaction. And we know that's not the case. That means this one has to be an oxidation reaction. To indicate that, essentially all I'm going to do is I'm just going to flip it, okay? So I'm actually going to kind of erase this one. So I said, put that comma back there. So I've got Ni. Ooh, I see what I did. Get that G back there, get that comma there, okay? So I had Ni. If I'm flipping around, I'm going to end up with +2 nickel there, plus 2 electrons, right? So now I flipped this reaction around. So I'm starting with the neutral nickel, I'm ending with the nickel ion. I need to switch this around. So this isn't negative 0.26. It's now positive 0.26. When you flip the reaction, you flip the sign on the reduction potential. So if this was already positive, when I flipped it, this now becomes negative. That's just how you do it. One thing I can do now, there's two things I can do right away. I can figure out what's my actual equation here and what's my total reduction potential. I'm actually just going to find the total reduction potential first. So my total reduction potential here is going to be positive 0.8 volts, and I'm just going to add the second one, plus positive 0.26 volts. That gives me a total reduction potential of 1.06 volts. The big thing here is your number should always be positive. Because even if both of our numbers were negative, like let's say that I had like negative 0.1, and then I was adding, like let's say I started with like negative 0.2 here. Well, when I flip this, this becomes positive, so then I'm adding a 0.2. I'm still going to end up with a positive 0.1. Right. My point here, though, is your total reduction potential will always be positive. Um, so that's a lot of voltage for a cell like this. So that's the first thing I would want to find is what's the total reduction potential. Essentially, once you just figure out which one's reduction, which one's oxidation, you can figure that out right away. The second thing we need is a balanced equation. Now to do this, I'm coming up here. I'm simply looking at these two things here. So my silver is taking 1 electron, my nickel is giving away 2 electrons. So really what I need to do here is I got to get my electrons balanced first off. So if I need 2 electrons here, I need 2 here. And in order to do that, I'm going to move that positive sign there. I need to essentially just double everything here. I've got 2 electrons here, 2 electrons here. Now I'm good to go. One of the things to remember though is just because I'm doubling the reaction up here, that's not going to change my number at all. All right, so now I've got 2Ag positive 1 ion. That 2 could be better. Plus this neutral nickel. And if you want, you include the plus 2E negative. Is becoming 2 neutral silvers plus 2 of the nickel ions. And once again, plus 2E negatives. But I now have 2 electrons on both sides of my thing. Those cancel out. So really, just know in the future, you don't need to include the electrons down here. Essentially, all of the ones I'm going to give you, your electrons are going to cancel out. You won't have any left over. So really, this is my balanced equation then. 2Ag plus Ni becomes 2Ag plus 2, Ni plus 2. Oh wait, I messed up. That 2 shouldn't be there. Because there's only 1. I accidentally brought a 2 down there. So, and this way I can see I'm starting with a total charge of positive 2 here. I'm ending with a total charge of positive 2. All right, so now the third hand, if I can get that to go away, is essentially I need to figure out what's the shorthand. So the shorthand for this is going to be I need to indicate what's undergoing oxidation, and then I'm going to indicate what's undergoing reduction. Okay, so it's going to look something like this. So the oxidation reaction is starting at the neutral nickel and is becoming the positive 2 nickel. So I've got neutral nickel, a line, and it's becoming the positive 2 nickel. That's all occurring in one beaker. Okay. I'm going to draw 2 lines to signify that I'm moving to the next beaker. In the other beaker, I have the silver that's starting charge. So I'm starting with a positive 1 silver, and it's becoming the neutral silver. That right there, that's the shorthand for this electrical chemical cell. With this information, I can actually figure out the rest of what's going on here. All right. There's a fourth thing I need to do, and that's to finish the diagram. So here we said the silver was taking electrons, the nickel was giving up the electrons. So with the way that I have the beaker set up, the nickel's giving away electrons, right? So my electrons in the wire, they're going away from the nickel because the nickel's becoming the positive 2 ion. That also means the nickel in this metal strip here is becoming the nickel ion. Essentially, the neutral metal strip is actually becoming negative ion in the solution, or positive ion in the solution. On the other side, I've got these electrons coming into the neutral silver stick. Okay, so what's going to happen is I've got these positive silver ions here. They're going to take those electrons and become neutral silver. Essentially, what we're going to see is this strip disappears and the silver strip's going to get bigger because these silver ions become neutral and kind of deposit onto the strip here. We're almost done. I need to keep what's in the beakers neutral though. So over on this side, I'm increasing the number of positive ions in this beaker. That means from the salt bridge, I need to counteract that addition of positive ions by adding negative ions to the solution. Over on this side, I'm losing positive ion, okay? And I can't take away from what's in the beaker, but if I'm losing positive ions here, if I want to keep this balanced, I just need to replace those positive ions. So in this case, since my salt bridge was sodium chloride, the sodium ions are going to go into the solution over on the silver side, the chlorine ions are going to the nickel on the other side. Clear as mud. So essentially the big trick here is going to be figure out your reduction potentials, whichever number's the bigger one, whichever number is the most positive number, however you want to word that, that's one undergoing reduction, the other one undergoes oxidation. From there, rewrite the other one like it's an oxidation reaction. Figure out your total reduction potential by just adding them together. Figure out the balanced equation, and that's really you're just looking at the electrons, make sure the electrons are the same in both reactions. Figure out your shorthand. It's essentially the oxidation goes first, the reduction goes second, and then just draw your diagram, signifying the metal strips, the solutions, what direction is the electron going in the wire, and where are my positive and negative ions from the salt bridge going to end up. That's all I'm going to ask you to do. So good luck with the practice problems, and let me know if you have questions.